Hello and welcome to yet another lecture on power generation and economics, paper code EE704C. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra, Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is Unit Commitment Solution Methods. The method is Priority List Method. Lesson objective. After end of this topic, student will able to understand the concept of unit commitment solution using priority list methods. So our topic is the unit commitment solution method. Today we will concentrate on priority list method. So from the name it is clear that we have to prepare a list depending upon the priority. So on which we will give the priority. Our first conception is that we will give the priority on the full load average production cost. We will give the priority on full load average production cost. Means, say the n numbers of units are running in a system. Among those n numbers of units, we will make a list given the priority on full load average production cost. Means the unit which have the less ever full load average production cost, it will appear at the top of the priority list, or its priority is more, and in this way the entire table will be formed. So the unit commitment problem, which is very much difficult. So let us take some or follow some situation that we must establish a loading pattern for M periods. For M periods, we must establish a loading pattern. We have N units to commit and dispatch. This portion is much more important that the period is the M periods of load pattern and number of units are the N number of units to commit and dispatch. The M load levels and the operating limits on the N units are such that one unit can supply the individual loads and that any combination of the unit can also supply the loads. So from that, the demand is for the M loads level, and when the N number of units are there, it is clear that one unit can supply the individual load or any combination of the unit can also supply the loads. Means all the one unit will be in operation or combination of the units are in operation. This is the most important point, that units, a single unit can operate or combination of the units can operate in order to meet the load demand. So where N is the number of units and M is the period. So we are now going to establish a commitment by enumeration method, or it is called the brute force method. So the total number of combination that we need is like that. Say we have three units. We have three units that are operating. We have three units that are operating conditions, or that the units are operating. So we can write it unit 1, In this way, we can write it unit 1, unit 2, and unit 3. That is the unit. We can write unit 1, unit 2, and unit 3. So this is our say 3 unit. So we are dealing with the combination that we have already seen. So how many combination will be there? In order to keep in mind that a combination is that all the units are at off condition, this one. Another is the unit 3 is in running condition. So this one, only unit 3. 1 that is stands for the running condition and 0 it stands for the off condition. If we consider. Now another is the unit 2 is running condition and other units are off. Another is the unit 2 and 3 are in running condition and the other units are off. Another is the unit 1 is in running condition and the other units are off. Another is unit 1 and 3 are in running condition, other units are off. We are trying all the combinations. Another is the unit 1 and 2 are in running condition where unit 3 is off, and another is all the 3 units are in running conditions. So you will see that 1, 2, 3, 4, 5, 6, 7, 8. We are getting 8 combinations. We can easily nullify this condition. We can easily omit this condition because we are very much concentrate in order to meet the load demand, because either by, we have already seen, we can meet the load demand either by a single unit individually or the combination of the unit. So this stage means all the units are in off condition, so it can able to meet any load demand, so we can easily omit that particular combination. So the total number of combinations are there 1, 2, 3, 4, 5, 6, 7. So here we will see the total number of combinations are 7. So total number of units are 3 units. So we can write the total number of combination can be written as 2 to the power n, that is n is the number of units, minus 1. That is n is the total number of units, that is 3 units that we have already seen when it is operating. So total number of combinations is 2 to the power 3. Total number of combinations is, can be easily found that it is 7. So total for the 3 units, it is total number of combinations are 7 that we have already seen, 1, 2, 3, 4, 5, 6, 7, whether the units are in running condition in order to meet the load demand. So the total number of combination that we need, that is Cn comma 1, n number of units, plus Cn comma 2, plus up to Cn comma n minus 1, plus Cn comma n equal to 2 to the power n minus 1, that we have already seen that total for the 3 units, total number of combinations are there is the 2 to the power n minus 1, that is 2 to the power 3 minus 1 equal to 7. So total number of combinations in order to meet the load demands are 2 to the power n number, 2 to the power n minus 1, where n is the total number of units. Now, where Cn comma j is the combination of n items taken j at a time. It is the n items from where we are taking j at a time. So it will become Cn comma j equal to n factorial divided by n minus j factorial into j factorial. So j factorial can be written as 1, 2, 3 is the multiplication of 1 into 2 into 3 up to j. So where we are taking the combination of n items and taken j at a time. So for the total period of m intervals, the maximum number of possible combinations is 2 to the power n minus 1 to the power m. So the total for the m intervals, the total combination is 2 to the power n minus 1 to the power m, 2 to the power n minus 1 to the power m. So now for the example, if I take the 24 hours combination, that is m equal to 24, and consider the system with 5, 10, 20 and 40 units, means n value is 5, n value is 5, 10, 20 and 40, where m value is 24. The table became n and 2 to the power n minus 1 into 24 equal to, for the 5, it will be 6.2 into 10 to the power 35. For 10, it will be 1.73 into 10 to the power 72. For n equal to 20, it is 3.12 into 10 to the power 144. For 40, it is too big. Now, there are very large numbers are upper bounds for the number of enumerations required. Fortunately, the constraint on the units and the load capacity relationship of typical utility systems are such that we do not approach these large numbers. Nevertheless, the real practical barrier in the optimized unit commitment problem is the high dimensionality of the possible solution space. The main problem lies in the unit commitment is the high dimensionality of the possible solution space that we are already seeing from that particular table, where we have chosen the total number of units are 5, 10, 20 and 40. For the 40, the calculation is too big, so it is high dimensional of the possible solution space for the in order to optimize the unit commitment problem. So the most talked about the techniques for the solution of unit commitment problem are priority list scheme, dynamic programming, Lagrangian relation. So the priority list scheme, dynamic programming and Lagrangian relation. So today we will concentrate on the priority list scheme. So the priority list method, we are taking an example, that is we are saying that is example 1a, that for unit 1, the minimum demand is 150 megawatt and maximum demand is 600 megawatt. And the H1 that will be given by the equation, this equation in MBTU per hour. For unit 2, that is the minimum demand is 100 megawatt and maximum demand is 400 megawatt, and H2 that is given by that equation, and that for the unit 3, the minimum demand is 500 megawatt and the maximum demand is 50 megawatt and the maximum demand is 200 megawatt, and the H3 is given by that equation, where the fuel cost are generally given 1.1 rupees per MBTU for unit 1. For unit 2, it is 1.0 rupees per MBTU. For unit 3, it is 1.2 rupees per MBTU. So we are very much concentrate on the maximum demand and the minimum demand of each unit. For the unit 1, it is 150, the minimum demand, and the maximum megawatt, and the maximum demand is 600 megawatt. For unit 2, the minimum demand is 100 megawatt, maximum demand is 400 megawatt. And for unit 3, the minimum demand is 50 megawatt and the maximum demand is 200 megawatt. So this is given in that particular example, and the corresponding cost of the fuel for the unit 1, 2, and 3 are also given along with the these are also given in this problem. So first of all, and also the how the units are consuming fuel generating unit at a specific rate, that is MBTU per hour, is also given in this equation. How the generating units consume fuels at a specific rate, that is also given in this particular example. So now we will concentrate on the another example, that it is given that this example that we have already known, that all the units and the fuel costs that are same in the example 1a, with the load varying from a peak value of 1200 megawatt to a value of 500 megawatt. To obtain a shutdown rule, simply use a brute force technique, but in all combinations of unit will be tried in example 1 for each value taken in steps of 50 megawatt from 1200 to 500 megawatt. All the result that is shown in the that we are applying the brute force technique, and it is given in the table 1.2. So simple shutdown rule that we have already applied, and we have already known that particular thing, when the load is above 100 megawatt, we will run all the three units. Between 100 megawatt and 600 megawatt, we run unit 1 and 2. And below 600 megawatt, this part is very much important, that we have already done, that the below 600 megawatt, we only run the unit 1. That is our previous general brute force technique in order to do the shutdown rule. So we have from a table where we have seen that up to 1000, the interval, we are moving from 1200 to 500 with a interval of, or say with a steps of 50 megawatt, and it is seen that up to 1000 megawatt, when it is 1000 megawatt, unit 3 is off. When it is given on the 600 megawatt, only unit 1 is running. This portion is very much important. When you use the simple rule of brute force technique, or that you are applying the conception of brute force technique with the help of simple shutdown rule, it is clearly seen that when the load is at 600 or below the 600, only unit 1 is there in the system, or it is in the running condition, and other units get off. Again, I am repeating, when the load is 600 or below the 600, only unit 1 is at the running condition with the help of the shutdown rule, simple shutdown rule. But now, today we'll see that how priority list scheme comes into the play, or with the help of the priority list scheme, how this conception is changing below the 600 megawatt load demand, which units are in running conditions. Only we have seen that simple shutdown rule, only the unit 1 is in running conditions. Here, only for these two, only unit 1 is in running condition and other units are off. But today, with the help of the priority list scheme or priority list method, today we will see that below the 600 megawatt or from 600 megawatt, how the shutdown will change of generating units. So, the simple unit commitment solution method consists of creating a priority list of units, and these priority lists are Now we saw in example 1b, a simple shutdown rule or priority list scheme could be obtained after an exhaustive enumeration of all unit combinations at each load level. The priority list scheme of example 1b could be obtained in much simpler manner by nothing the full load average production cost of each unit, where full load average production cost is simply the net heat rate at full load multiplied by the fuel cost. The value of H1, H2, H3 that we have already seen in the example 1a, which are given the net heat rate, which is the simple multiplication of net heat rate, that is H1, H2, and H3 in that example 1a that we have already seen for unit 1, unit 2, and unit 3. Those three heat rate simply multiply by the full uh, fuel cost that we have seen for unit 1, unit 2, and unit 3 at full load. So we have to create a list. In that list, we have to give a priority of units, and this priority is given on the basis of full load average production cost of each unit. And it is clear that the unit which have less the unit which have less full load average production cost, we have to give most priority or topmost priority to that particular unit, and it will came at the top of the table the unit which have less or minimum full load average production cost. Again, I am repeating, the unit which have minimum full load average production cost, it will give the topmost priority, or it will come at the top of the list of all units with the help of or with the applying the conception of priority list method. So a problem that we are given that obtain the priority list of unit commitment using full load average production cost for the power demand of 500 megawatt. Our power demand is 500 megawatt. So let us we are taking the same example where H1, H2, and H3 are generally given by the net heat rate, and corresponding it is for the unit in MBTU per hour for unit 1, unit 2, and unit 3. That is unit 1, unit 2, and unit 3. The loading limit, that is the minimum load for unit 1 is 150 megawatt and maximum is 600 megawatt. For unit 2 it is 100 megawatt and 400 megawatt. For unit 3 it is 50 megawatt and 200 megawatt, and the corresponding fuel costs are 1.1, 1, and 1.2, and where it is the H1, H2, and H3 are the net heat rate. So in order to find we have to find the full load average production cost. It is nothing but the multiplication of that we have already seen that the full load average production cost is simply the net heat rate at full load multiplied by the fuel cost. So this is the net heat rate which is multiplied by the fuel cost in each unit. And then we have to give the priority that which unit has less full load average production cost. So that is the calculation for full load average production cost. So that is the full load production cost, that is the average production cost for the unit 1. It is nothing but this is the net heat rate. So it is 510 plus 7.2 into 600 plus 0.00142 into 600 square. The total will be multiplied by 1.1. divided by 600. So it is clear that total, that is total for the P1, it will be P1 equal to 600. So that equation where the P1 is replaced by the 600 and P1 square is replaced by the 600 square, and total, in order to find the average full load production cost, that is the multiplication of net heat rate at full load, which is H1, which is multiplied by the fuel cost, that is 1.1, and divided by 600. So we are finding that the average full load production cost is 9.79. So same for the unit 2, where we can write P2 equal to 400 and it is multiplied with 1 divided by 400. So it will 1 into 0.00914 into 400 square plus 7.85 into 400 plus 3110 divided by 400. So you will getting 9.4, the average full load production cost of unit 2. Now for the unit 3, where P3 is replaced by 200 and P3 square is replaced by 200 square. So it is 1 and it is totally multiplied with 1 by 1.2, the fuel cost. So it is 1.2 into 7.80 plus 7.97 into 200 plus 0.00482 into 200 square. This is the result, that is divided by 200, and we will get the average full load production cost is 11. So for the 3-unit system, we have seen the 3 different values of average full load production cost. So if I want to give the priority, so we will give the priority to that particular unit which have less or minimum value of the average full load production cost among the 3 production cost, among the 3 full load average production costs. So it is clear from that equation that unit 2 has a minimum value of average full load production cost. So using the conception of priority list method, unit 2 will be given the topmost priority, followed by unit 1 and followed by unit 3. So a strict priority order for these units based on the average production cost will be given as follows. So that is the priority list that we have developed depending upon the average full load production, full load average production cost. So depending upon the full load average production cost, so unit 2 is given the topmost priority, where the full load average production cost is 9.4, minimum generation is 100 megawatt, maximum generation is 400 megawatt for the unit 1, followed by the second priority will be given to unit 1 depending upon their full load average production cost, that is 9.79, and its minimum generation is 150 megawatt and maximum generation is 600 megawatt. Now the unit 3 at the 3rd position in the priority list, because it has a the value of average full load production cost is highest among the 3 units, so it is 11, and the minimum value is 500 megawatt of generation and maximum value is 200 megawatt. So in this way we can form the priority list table depending upon the average full load average production cost. So minimum value of the full load average production cost of a unit, it will come at the top of the priority list. Now the unit commitment. So when the combination of 2 plus 1, it is clear that when the 3 units is in running condition, look at the combination. It is not written as 1 plus 2 plus 3 or 3 plus 2 plus 1. It is written as 2 plus 1 plus 3, means we have to first make unit 2 on, then unit 1, then unit 3. So the minimum demand will be 300 and the maximum demand, the summation of that 3, and the maximum demand is summation of the 3, it is 1200. When the 2 combination is there, first we have to on the unit 2, commit the unit 2, then followed by the unit 1. So it is total summation of these 2, that is 250 is the minimum demand and maximum demand is 1000, that is summation of 400 plus 600. Now And when a single unit is in running condition, it is clear that uh, the unit 2 is in running condition, so it is minimum demand is 100 and maximum demand is 400. So when we have to run a single unit, we have to run the unit 2. So our problem is that to meet the load demand of the 500 megawatt, unit 2 and 1 should be committed, because the 500 megawatt load demand is lies between the range of 200, 250 and 1000 megawatt. So 500 is lies between that 250 and 1000 megawatt. So in order to meet the load demand of 500 megawatt, unit 2 and 1 should be committed. Main thing is the sequence. It is right, it is written in the sequence of 2 plus 1 plus 3, means unit 2 we have to commit, followed by unit 1, followed by unit 3 when the 3 unit is in running condition. And when the 2 units are in running condition, first we have to commit unit 2, then unit 1. When a single unit is in running condition, we have to commit the unit 2. Say we have a load demand of 200 megawatt, we think that we can easily run the unit 3 because it can capable of meet. Say we have a load demand of 150 megawatt, it is lies between 500 and 200 megawatt, so we can easily think that we can easily run the unit 3 and meet the load demand, or we can easily commit the unit 3 and meet the load demand, but it is not possible depending upon the priority list method, that the value of the full load average production cost is more for the unit 3. So we can't run unit 3. We have to run unit 2. So because it has less or the minimum value of full load average production cost. So in case of the example 1b that we have already seen, that the general shutdown scheme, that where unit 2 was shut down at 600 megawatt, leaving unit 1. Now, when we apply the conception of priority list scheme, that for when we are using the conception of priority list scheme, we will see that when a single unit is running, we have to run the unit 2. So up to 600, up to 400 megawatt, we have to run the both unit, that is unit 1 and unit 2. And then means until the load that is dropped to 400, we have to run those both 2 units. Then unit 1 should be dropped and unit 2 should be in the running conditions. So means if I go to that particular table, it is a simple shutdown table, that the shutdown rule that we are applied, that below 600 megawatt run only unit 1. So it is clear that below the 600 to 600 megawatt, all the units are off and unit 1 is in running condition. It is a simple shutdown rule. Now we are using the conception of priority list method. Means we are given a conception of full load average production cost. So if I see that particular table for the full load average production cost that we have already seen, that unit 2 have to run first. So means when the load is dropped up to 400 megawatt, it is clear that both of the units will be in running conditions. So from 600 to 400, here is a change is there. This off, all this off will be become on. Up to 600 to 400, both we can say that, in other words, we can say that up to 600 to 400, both the units in on condition. Unit 1 is on, say it is unit 1 and unit 2. So it is on and it is on. So below the 400, below the 400 to 400, it is clearly that unit 1 is off and unit 2 is on, depending upon the priority list method, when a single unit is there, say for the 350 load, again the same thing is repeat. Unit 2 is 1 is off and unit 1 is on, because below 400, from 400 to 4 to 0 to 400, we have to run the unit 1 and we have to run the unit 2 and we have to off the unit 1 in this way, because it is clearly seen that the unit 2 has a minimum loading limit is 100 and maximum loading limit is 400. So the load that is lies between the 100 to 400, we have to run the unit 2. In the previous problem of simple shutdown rule, that below the 600 only unit 1 is running, but it is after applying the knowledge of priority list method, we are seeing that from 600 to 400, both unit 1 and unit 2 is in running condition. Now when the load comes below 600, and when the load that is comes below from 600 to 400, unit 1 and unit 2 both are in running condition. And when the load that is falls below 400, unit 2 is in running condition and we will off the unit 1. Both units will be held on until load reaches to 400, then unit 1 should be dropped. That we have already seen. That from 600 to 400, both units are in running condition, and up below the 400, unit 2 is off and unit 1 is off and unit 2 is on. So the load that is below 400, where all these cases that unit 1 is off and unit 2 is on condition, depending upon the, by applying the conception of priority list method. This is the difference that we have seen when we use the conception of simple shutdown technique. In case of the simple shutdown technique, that is the load that is from 600 megawatt to below 600 megawatt, we are only commit unit 1 in order to meet the load demand, but using the help of priority list method, it is clearly seen that from 600 to 400 megawatt load demand, unit 1 and unit 2 is in running condition. Now below the 400, from 400 to below the 400 megawatt, only unit 2 is in running condition, unit 1 is dropped, and it is totally depend upon the priority list method, where the minimum value of the full load average production cost of the unit 2, which make it commit, which make the unit 2 commit below the load below 400, and we have to drop the unit 1. So this difference that we have already seen using the conception of least priority method, and the combination are given that in which order the unit will be turned on. 2 plus 1 plus 3 means 2 will turn on first, then 1, then 3 when the 3 units are in running condition. When the 2 units are in running condition, we have to run unit 2, then unit 1. And when the only single unit is in running condition, we have to run the unit 2, depending upon the priority, by applying the knowledge of priority list method. So the simple shutdown algorithm is that priority list scheme are built around a shutdown algorithm that might operate as follows: that at each hour when load is dropping, determine whether the dropping the next unit on the priority list will leave sufficient generation to supply the load plus spinning reserve requirements. If not, continue operating as is. If yes, go on to the next step. The next step says that determine the number of hours H before the unit will be needed again. That is, assume that the load is dropping and will then go back up some hours later. If H is less than the minimum shutdown time for the unit, keep commit as is and go to last step. If not, go to the next step. Calculate two costs. The first is the sum of hourly production cost for the next 8 hours with the unit up. Then recalculate the same sum for the unit down and add in startup cost for either cooling the unit or banking it, whichever is less expensive. If there is sufficient saving from the shutting down the unit, it should be shut down, otherwise keep it on. Repeat this entire procedure for the next unit on the priority list. If it is also dropped, go to the next and so forth. This is the simple shutdown algorithm. So today we learn about the priority list method. That is one of the important method of unit commitment solution methods. And we will also see that how the full load average production cost will determine the which unit we have to give the priority. So the priority list method means all the units that we have are in operating condition. We have to provide a list of these units, or uh, means that the list of that unit will be given depending upon the priority, means which unit will give the most priority, and this priority will be given based on the full load average production cost, means the unit which have minimum full load average production cost, this unit will give the most priority and followed by the other units. So today we learn about the priority list methods. Thank you.